Okay.
motion and electrical section of this exhibit, the relevance of mass.
Okay.
Part of it is also how what those people are doing, what that represents in their kind of efforts and search and investigation and innovation, and then how that kind of is characterized in the group that we work with.
Okay.
And we'll talk about some of the general principles that are represented in the exhibit, like dynamics and so forth, and then
Okay.
you can give me examples of the issues that we talk about and how they
Okay.
sort of look forward to
Sure.
bring it back to UTC, what we're working on now, things that we're investigating, that's needed.
Okay.
The fact that the world's becoming more electrical.
Okay.
Okay. All right. So we'll begin.
Yeah.
Good. Okay. So how do the pieces of the electrical motion section relate to some of the technologies that UTC is involved in today?
Okay. Motion is a key element of UTC products. If you look at some of the things that we make for carrier, like compressors, they're all motors are integral part of compressors, and that converts electrical energy into motion to drive some of the components inside a compressor. Same thing for an Otis elevator system. You have electrical energy that's converted to motion to transmit passengers up and down a building. And you can see various other examples in products that we make where motion, especially electrical motion, is a key component of the kind of things that we do. So how do we do them better? How do we have the right performance? How do we tweak the electrical components to get what we need? Are all things that we investigate, that we try to have innovations around to make sure we give the right product to our customers.
Well, let's see.
Yeah.
Do you have a separate set of phones?
You can have
I'm having trouble because
That's
there's so
fine.
much
No.
signal in I got it.
No, you can have those.
Sorry, I'm
I
gonna
can
go.
watch. I know what it sounds like. I can watch it.
Yeah, it's just.
And also sometimes when you're speaking, it's hard to hear you as well.
Yes, right.
Yeah.
Signal and noise. Right. Yeah. Okay. So I wasn't quite 100%. As this is the last answer. Yeah. Okay. Now I can hear you.
Okay.
And I'll make my questions a little louder.
Okay.
That's your phone's on it, so.
Yeah, somehow that mic dropped in just a bit.
I slid it a little closer. That's why.
Sorry.
It also looks like it's a little. It also looks like you've got no windows.
Or like
It's
that.
not the way he's talking. It looks like it's off axis.
Right about there.
A little bit more. That's good. Perfect.
Thank you.
Now, it's bouncing in, but I think there we go. I got it.
We're rolling.
Okay. So what's important and what do you gain from looking at the past when you're trying to solve the problems today?
I mean, it's fascinating to see what was done in the past, how the innovators, put together concepts that kind of define the products that we do right now. If you look at some of the elements in the museum display, you can see an Ørsted's demonstration apparatus that kind of shows the first time when electrical energy was converted to motion by placing it next to a magnetic field. And if you look at that very simple but powerful demonstration, you can directly relate that to some of the motors that we do right now for Otis, Carrier, or for our aerospace business, where again we are looking at current going through coils in the presence of magnetic fields, causing motion. So there are lots of elements that we can see in the past as to how the innovators put things together that allow us to understand fundamentally the physical principles that govern the various products that we put together. And the innovators in the past did not have the powerful computers and equipment that we are so used to seeing right now. So to look at how they use their creativity to put things together is just mind-boggling. I mean, we are so used to computers and running simulations the whole time that to do hand calculations and see what they came up with is just amazing.
Is there a particular instrument in the thing that relates to you personally?
I mean, there is one that I'm very fond of, and that's the Helmholtz tangent galvanometer. It's basically an apparatus that measures the amount of current going through a physical coil. A lot of the things that we do right now depend on our precise measurement of electrical quantities, and this is an instrument that does that. For me, this is one of the instruments that I built in high school as part of my high school physics project. It's one of the things that I learned, and one of the reasons why I became an engineer in the first place is where I could, build an instrument that measured something so accurately and so precisely. And when I saw this instrument in the display, it kind of reminded me of why I became an electrical engineer in the first place. It's just impressive to see the original right there in the museum.
What are some of the common themes that you think between investigators and scientists and innovators of the past and kind of how you work today?
I mean, fundamentally, an engineer is a problem solver. So we are faced with something that we want to do. We understand the physics behind the various phenomena that govern that particular application, and then we try to find ways in which we can make things put together to make things happen. And if you look at some of the equipment that is on display and some of the instruments, you see the innovators in the past do exactly the same thing. They're faced with a challenge, they come up with the principles that they need to solve, and equipment that actually demonstrates those principles. And we follow that same procedure even now in solving some of the hardest problems that you see, making a jet engine work more efficiently, or making an making an airplane fly. I mean, all of these have the same problems that we are trying to solve as was done in the past. So it's kind of grounded when you see, it's grounding for us when you see what people have done in the past and how we can relate to those and do a better job right now.
Can you describe some of the scientific principles in the electrical section, name a few, and then we'll talk about some of the instruments and examples?
Sure. I mean, the electrical portion of the display is divided into two main components, into electrostatics and then electrodynamics or electromagnetics. So essentially in the electrostatics portion, we have a bunch of equipment that kind of displays what static electricity can do, how do we realize the impact of static electricity, and how do we define or design equipment to mitigate any potential drawbacks that we might have. The second part of the display has electrical energy in motion in terms of electromagnetism. And so basically a flowing electric charge produces current, and so the artifacts on display show what we can do in terms of motion with those type of equipment. So fundamentally, if you look at that, we have electrical energy being converted to mechanical energy, or mechanical energy being converted to electrical energy through generators. And in each portion of the display, in the electrostatics as well as electromagnetics, we have measurement equipment that shows us how we can precisely measure these quantities that allow us to define systems that are guarantee the performance that we want in our field application.
So can you talk about some of those instruments, for example, Kelvin's device?
Sure. So if you look at it in the museum, we have a Kelvin quadrant electrometer, which is a very precise instrument for measuring electric charge. If you look at some of the equipment that we do right now in terms of energy storage elements like batteries, knowing how much energy storage is there in the battery and how much you're pulling out is key in defining lifetime of our equipment, in defining the performance of our equipment. And so the electrometer gives you a window into how those principles are realized in a measurement equipment or instrument for us to define our performance goals. So it's a beautifully done instrument, defining and showcasing a lot of the principles that we do right now in a different form, of course, for our modern day equipment.
How about Ampere's demonstration?
Right. The shirt?
That's what. Is this what you want? Is that good? Okay. Did you do that?
I just did it right now. I thought you guys are saying shirt and pointing here. I was like,
Yeah,
okay.
that's because they.
Stop and start.
So is that good